Bem, o próximo conferencista é um grande amigo do Brasil, um grande amigo nosso em particular, Dr. Michael Lederman, professor Scott, ele é Scott Enkley Professor of Medicine e diretor do AIDS Research Center da Cleveland University, Case Western University. Ele é editor de Patogênese and Immunity, e entre seus títulos ele não costuma incluir alguns de menor valor, mas nós devemos lembrar que ele também é um ótimo pianista, especialmente depois que ele comprou um piano novo. E se vocês tiverem ocasião depois no hotel de pedir para ele tocar Chopin ou Schubert, eles vão ser bem recompensados. Dr. Lederman, please.
Thank you, Guido. It's very good. You'll be very pleased to hear that I will not be playing the piano for you. One I've been playing for most of my life, and I do it because I enjoy it. But there's an added benefit in that when I practice, it drives my wife crazy. She hates it. So thank you, Guido, for that kind invitation. Esper, thank you 1,000 times for inviting me here to Brazil again. I'm going to talk to you a little bit about inflammation and morbidity, specifically cardiovascular risks. So without further ado, okay, first my conflict of interest statement. My brother Robert is a cardiology researcher at the NIH, and we've been competing for our parents' attention for more than 50 years. All right. So the story I'm going to tell you is that, and I've given parts of this before, but the data that I'm going to show you today includes some new things that have been published since, and some things that are not yet published. So the model that we like is that there is an inflammatory procoagulant environment that we see in both treated and untreated HIV infection that promotes cardiovascular disease. And we think that this does so. You know, I don't care if plasma IL-6 is high or plasma IL-1 beta is high. Who is doing the damage? And we're saying that the damage is mediated by an accumulation of monocytes and CD8 positive T cells at the endovascular surface, and that these cells, these elements, collaborate in the formation of atheromatous plaque and vascular pathology. It's a good story. The fact of the matter is we know already that the vessels in the aorta and other vessels in HIV disease are inflammatory. We hear that they take up glucose, fluorodeoxyglucose in a PET scan. The differences between the HIV, let's see, between the HIV negative individual and the HIV positive individual in terms of intensity of stain are simply, of uptake are dramatic. And you should know that, at least I'm assured by the radiologist, that the cells that take up this glucose in this setting are not T cells, not B cells, but they're monocyte macrophages. So we know that there's uptake of glucose by cells that are likely to be monocyte macrophages at these sites. I'm going to tell you, briefly introduce you to monocytes and macrophages in HIV infection, but I'm going to spend most of the time today talking about CD8 T cells. Monocytes, circulating monocytes, can be divided into multiple populations, but the two that are most important in terms of cardiovascular risk are ones that are inflammatory, capable of elaboration of inflammatory mediators that we can measure in plasma. Although, by the way, do you know where your IL-6 molecules in plasma come from? Do they come from circulating blood cells, or do they come from other sites? The answer is you don't. Nobody knows, but we've made these assumptions that they all come from circulating blood cells. May be true, but I don't really know. But nonetheless, the cells that we find in circulation are inflammatory, capable of making these things if we stimulate them, or capable of making them spontaneously, and cells that we call patrolling monocytes. And the patrolling monocytes are monocytes that have high density of a receptor for fractalkine. That receptor is CX3CR1. You'll hear more about that in a moment. And these fractalkine receptor positive monocytes can bind to fractalkine, can chemoattract towards fractalkine, and fractalkine is typically expressed CX3CL1 on endothelial surfaces. So these guys make cytokines. They can do so in response to bacterial products. They can do so in response to oxidized lipids, such as oxidized low-density lipoprotein, and then they can do so in response to viruses and viral sequences. And importantly, they're enriched for expression in HIV disease. They're enriched for expression of a character called tissue factor that I've talked to you about before. This is a picture of it. Tissue factor on the surface of the cell, which activates factor 7, a soluble coagulation factor in circulation, and ultimately results in this zymogenic protease-mediated cleavage of preproteins that generates the coagulation cascade, and finally ends up with a molecule called thrombin, and we'll talk more about thrombin in just a moment. Monocytes also express the fractalkine receptor, as I've mentioned, that allows them to accumulate on the endovascular surface, and there's reason to implicate monocyte activation as playing a role in cardiovascular risk, since soluble factors linked to monocytes, soluble CD163 and soluble CD14, are linked to cardiovascular disease and treated HIV infection. All right, so CD8 T cells. What is their relationship to cardiovascular disease and in HIV infection? First off, one of the things that's most impressive about HIV infection, and we heard about this yesterday, I think it was Hendrik who showed these data, that CD8 T cell numbers are expanded in HIV disease. And the differences are dramatic. The average CD8 T cell number in an HIV negative person sits around 500 or so per microliter, but on average in HIV positive individuals, even with years of antiviral therapy, the average CD8 T cell count is over 1,000. So there's a dramatic expansion in the numbers of circulating CD8 T cells in HIV disease. These cells are matured effector cells by phenotype, and I've shown you these data before. They're said to be senescent, and Alan talks a lot about senescence because he's really old. But I'm not sure they really are senescent, and they are clearly inflammatory. If you stimulate them and if you look at them, just look at them funny, they'll make inflammatory cytokines. Importantly, these expanded CD8 T cells are not HIV reactive. They're not responding to HIV peptides, and particularly in the setting of long, and Hendrik made that point earlier, but certainly in the setting of long-standing antiretroviral therapy, when there's not much HIV antigen floating around, these are not HIV reactive cells. Their activation, straight out of the blood, reflected in a lot of ways, but classically by co-expression of CD38 and HLA-DR, predicts rapid disease progression in untreated patients. And in the treatment era, a low CD4 to CD8 ratio, which is comprised of low CD4 cells, but even if the CD4s are normal, if the CD8s are high and the ratio is low, this predicts morbid outcomes in the setting of antiretroviral therapy, and numerous studies have demonstrated as much. So, a couple of questions. First off, why are CD8 T cells expanded in HIV infection? 2, how does this expansion in maturation and differentiation link to cardiovascular disease, or does it? And 3, and this is specifically for Alan, the senescent person in the front row, if these CD8 T cells are senescent, how and why do they persist? What keeps them around if the numbers are so high? And these are the numbers. This is Sergio Serrano Villar's study looking at the CD8 T cell numbers in 2 settings of people with HIV disease. The first one is people who received antiretroviral therapy early, and these are the numbers of the individuals. And you can see that on median, they drop a little if they start antiviral therapy early. But they don't drop a lot. They're still really high. If we treat later, and this first bar area represents the period of time at which they are not treated, you can see that these cells expand in numbers. They drop a little bit, but they still stay high. They still stay over 1,000 over years and years and years of therapy, and I showed you the cross-sectional data before. So what is going on? Well, first let's talk a little bit about the phenotype of these cells. In HIV infection, irrespective of the antigen specificity of the CD8 T cell, that is completely unrelated to what peptide they recognize, cells, CD8 T cells of people with HIV infection are capable of cytolysis based on phenotype here. So on these dot plots, we have a healthy control on top, an HIV positive person untreated on the bottom. The y-axis in each instance represents cells reactive with a particular tetramer peptide complex. Here, HIV peptide. Here, influenza peptide. Here, CMV peptide. And so the guys on the bottom are all the CD8 T cells. The guys on the top are the ones that are specific for those tetramers. The healthy control, of course, has no HIV-reactive CD8 T cells. Some influenza-reactive CD8 T cells, some CMV-reactive CD8 T cells. This is the proportion on the x-axis that express granzyme, which is one of the important cytolytic molecules. You can see for CMV, which is a fairly active infection, even in people who don't have cytomegalovirus disease, there's continuous expression of CMV himself in various sites of infection. The majority of these cells, 0.54 versus 0.18, are granzyme positive. But look at what we see in the HIV positive person. These are all granzyme positive, virtually all granzyme B positive. And it's not just the prevalent antigens like CMV and HIV here, even influenza. And this particular sample was obtained, as most of these particular samples were obtained, in the non-influenza season, a self-limited virus infection. All the remaining influenza-reactive cells are granzyme B positive. And you can see that in the bottom figures, where these are all specificities. The majority of all the CD8 T cells are capable of expressing granzyme. These are straight up ex vivo. All right, how does this happen? Well, we looked at a variety of plausible drivers of this cytolytic capability. We looked at the ability of IL-2, IL-7, IL-1 beta, IL-6, IL-15. Many of these have been implicated in HIV pathogenesis, and IL-15 to upregulate expression of granzyme B on total CD8 T cells and CD8 T cells that on the y-axis bound CMV peptides. And this is from a healthy control. This is not from an HIV positive person. And we can see that in the absence of cytokine, very few of these, in this particular instance, very few of these cells were CMV reactive, and even fewer were reactive with this peptide, and even fewer expressed granzyme B. And this could be upregulated not by IL-2, not by IL-7 very much, not by IL-6, not by IL-1 beta, but dramatically by interleukin-15. So interleukin-15 can induce a potentially cytolytic phenotype on cells of a variety of specificities, and we can see that in the other population here, where we go from 11% to 27%. These are CMV specific, these are all the other specificities in circulation. So together with Jake Estes, we looked at the lymph nodes of these persons with HIV infection and healthy controls and stained for interleukin-15. Here is the staining of a healthy control, the staining in an untreated patient with HIV disease, and this is an HIV-infected person after antiretroviral therapy. And these are the summary data, IL-15 on the y-axis, healthy control here, untreated patients here, HIV-positive patients under antiretroviral therapy. And we found that there is a good relationship between the lymph node expression of IL-15 and the absolute numbers of CD8 T cells. So we think that during uncontrolled HIV infection, there is an expansion of CD8 T cells that could be mediated by exposure to interleukin-15. Now, as cells, CD8 T cells mature from a naive to central memory, to effector memory, to an effector memory terminally differentiated phenotype, they increase their expression of that fractalkine receptor, CX3CR1. We don't see this much on CD4 cells. We see this substantially on CD8s, and these proportions go up as these cells become increasingly mature. So when you're young, you don't want to hone to the endothelium, but as you get a little older as a CD8 T cell, you like to do that. IL-15 can induce this phenotype. IL-15 exposure upregulates CX3CR1 expression in vitro. IL-15 exposure also substantially increases the maturation phenotype of CD8 T cells, upregulating expression of CD57, which we consider a, quote, senescence marker. I'm not sure that it is. Reason for my skepticism will come out a bit later. But in every phenotype of cells, 57 positive, 28 negative, 57 negative, 28 negative, and 57 negative, 28 positive, we see upregulation of CD57. IL-15, as I showed you earlier, upregulates granzyme, but here we also see that it upregulates expression of perforin, another key enzyme necessary for the cytolytic event. And finally, and this is important too, and we'll see this later when we talk about the cells that are actually isolated from the plaque, IL-15 makes CD8 T cells upregulate expression of CD69. And CD69 is a critical element that keeps cells in tissue. It keeps cells in tissue by blocking access of the sphingosine 1-phosphate receptor to the cell surface, which is what cells use to migrate from tissues into blood. Okay. These, if we look at, now we're looking at people with HIV infection who have a high number of cells expressing the fractalkine receptor here. These cells are typically CCR7 negative, which means they don't want to go to lymph nodes. They're CX3CR1 positive, treated HIV versus HIV negative. When we look at these cells in lymph node and blood, none of these CX3CR1 positive cells are in the lymph nodes, but they're kept out of the lymph nodes, they're kept in circulation. And we see a relationship between CX3CR1 positivity and the ratio, a low ratio of CD4, CD8. So the lower your ratio here, the higher the proportion of your cells are that are matured expressing fractalkine receptor CX3CR1. CX3CR1 is a vascular homing receptor, and again, the question is, are these cells in the blood vessels? We'll see soon. All right. Here's another important observation made by Michael Freeman, and that is that we only see CD8 expansion in HIV co-infected people who are CMV seropositive. Now, it's hard to find an HIV positive person who's CMV seronegative, but they do exist, and when Michael collected a bunch of them, we see their CD8 T cell numbers are around the average in the HIV negative population, around 500 per microliter. Yet the CMV seropositives are where we typically expect the CD8 T cell numbers, absolute numbers in circulation of around 1,000 per microliter. So the story I'm trying to tell you is that CMV co-infection is necessary to have an expanded CD8 T cell number, and in HIV disease, these numbers are expanded in those individuals largely by exposure during untreated infection to interleukin-15. All right. So now how do we put these things together? If we look here, when we look at a seronegative individual on the top and a CMV seropositive individual on the bottom, when we look at the frequency of cells that are CX3CR1 positive on the y-axis, those proportions are increased dramatically in the CMV seropositive individual, suggesting to us, and this is known from other data as well, that in CMV co-infection with HIV disease, the vast majority of the expanded CD8 T cells are more matured, have a matured, quote, senescent phenotype, and express this fractalkine receptor. And here we have these data in summary, where we look among the memory CD8 T cells, among the CMV seronegative, only a minority are CX3CR1 positive. Among the CMV seropositive, a substantially higher proportion are fractalkine receptor positive. When we look at CMV-specific cells, these cells are also enriched for CX3CR1. So before we were looking at all CD8 memory cells, now we're looking specifically at cells that respond to, that recognize a CMV antigen, PP65. Here we look at cells that recognize influenza. When we look at the CMV recognizing cells, a substantially high proportion of these cells are fractalkine receptor positive on the y-axis, and they also express PAR-1. The summary data are seen here for CMV-specific cells that are fractalkine receptor positive and PAR-1 positive versus Haemophilus influenza specific CD8 T cells. What's the significance of being fractalkine receptor positive and PAR-1 receptor positive? Well, here we see these numbers again, and I don't think we need to go over it, but the key point here is that PAR-1 is a cell surface receptor which is cleaved and activated by thrombin, and thrombin is that product of the coagulation cascade that is generated when the coagulation cascade is activated by things like tissue factor that's on the surface of monocytes. So here we see monocytes have tissue factor that activates the coagulation cascade. CD8, matured CD8s in HIV disease, CMV co-infection heavily express PAR-1, which is cleaved by an end product of coagulation, and both these cells, we think, accumulate on the endovascular surface because they express the vascular homing receptor, fractalkine receptor CX3CR1. Now, is that true? Yes. Here are the data that show in a SHIV positive rhesus versus a SHIV negative rhesus that we can find CD8 cells, CD68 positive cells, these are monocytes, coexisting, and this is what the H&E stain looks like in a SHIV positive versus SHIV negative, and these are the summary data of CD8 cells on the endothelium and CD68 positive cells on the endothelium, and in each instance, those frequencies, and they're hard to count, and it took a lot of work for Shomo Panigrahi to do this, they're much more frequent in the endothelium of the SHIV-infected animals, positive, than the SHIV negative animals, negative here, both for CD8s and for CD68s. How much time do I have? Oh, I'm good for time. Good. All right. What about humans? It's hard to get human blood vessels. But in models, when we look at aortic endothelial cells in vitro, we can see that they can express CX3CR1, no big surprise. But they also express interleukin-15, which we saw earlier, and we accused interleukin-15 of playing a big role in activating and expanding CD8 cells. But now it's not the lymph node. Now we see them in aortic endothelial cells. We see a little bit of them in aortic smooth muscle cells, and when we test them in vitro and look at their expression, we can show that the aortic endothelial cells are in red, the aortic vascular smooth muscle cells are in blue. We can see that they express the ligand for CX3CR1, which is CX3CL1 or fractalkine. The endothelial cells do a lot of it. The smooth muscle cells don't do nearly as much. They both make the interleukin-15 cytokine, but only the vascular endothelial cells make the cytokine alpha chain receptor, which is needed in order to make the cytokine biologically active. The smooth muscle cells do not. And they release the IL-15 into the supernatant. So in vitro, we can show that these cells can elaborate both IL-15 that activates CD8s and the ligand for fractalkine receptor, which is fractalkine. What do we see in the aortas of SHIV-infected rhesus macaques? We see that the positive are SHIV-negative animals, SHIV-positive animals, SHIV-negative animals, SHIV-positive animals, and in both settings, the expression of the ligand for CX3CR1, which is fractalkine, CX3CL1, is increased, as well as expression of interleukin-15 is increased in the SHIV-positive animals. And these are the summary data of multiple animals. These are the individual micrographs, fluorescence micrographs. All right, so I think you're getting to the idea that I'm accusing CMV and interleukin-15 of potentially being damaging characters when it comes to cardiovascular risk. We talked a little bit about what IL-15 might do in the endothelium, that it's present in the endothelium. What does it do to these CD8 T cells? Well, first thing that it does is it promotes proliferation. IL-15 promotes proliferation of CD8 T cells, and we can do this. The x-axis represents the density of cell trace violet. In this assay, what you do is you incubate your cells with this dye, this fluorescent dye, and then you culture them for a period of time. And when these cells divide, each daughter cell gets half the amount of dye, and so we get dilution movement to the left on the screen. So what we see is that in the presence of IL-15, these cells dilute dye, and each one of these major areas is half the fluorescence intensity of the parent, and we see substantial proliferation. So it gets these cells to proliferate. At the same time, they upregulate expression of the fractalkine receptor, CX3CR1, that we can see on the y-axis. IL-15 does this. This is in the absence of IL-15. This is in the presence of IL-15. The number of cells that proliferate can be seen here in these summaries here. Proliferation is measured by dye dilution. And the proportion of cells expressing the fractalkine receptor in summary data are shown here, IL-15 versus medium. These cells are inflammatory. In the presence of IL-15, they can induce expression of tumor necrosis factor, not so much in the induction of interferon gamma. And these are the fractalkine receptor positive cells. These are total CD8 T cells that can be induced to express tumor necrosis factor by IL-15. Tumor necrosis factor is an important mediator of activation of endothelial cells. When we expose cells, endothelial cells, to tumor necrosis factor, the aortic endothelial cells upregulate expression of fractalkine, as measured by RNA, as well as by measurement in supernatant. And they, interleukin-15 tumor necrosis factor upregulates expression of interleukin-15 by the endothelial cells, upregulates expression of the alpha chain receptor, and tumor necrosis factor increases IL-15 expression. So these are bidirectional relationships, with TNF upregulating IL-15 and IL-15 upregulating TNF. So to summarize where we are right now, CD8 T cell numbers are expanded in HIV infection, likely driven by CMV co-infection and interleukin-15. These cells are matured effector cells with vascular homing, fractalkine receptor, and cytolytic potential, granzyme B and perforin, irrespective of antigen specificity. We can induce this phenotype in vitro by exposure. This maturation phenotype, cytolytic phenotype, and inflammatory phenotype can be induced by IL-15. IL-15 is expressed by vascular endothelium and smooth muscle, but only the endothelium makes a biologically active IL-15 that has the alpha chain receptor. Vascular endothelium in HIV infection is enriched for expression of both fractalkine that attracts and binds CX3CR1 positive monocytes and CD8 T cells, and IL-15 that can activate CD8 T cells. IL-15 activates CD8 T cells to make TNF that activates monocytes to express tissue factor. Did I show that? I don't think I did, but it does. It does. That activates the coagulation cascade to form thrombin that activates PAR-1 positive CD8 T cells. The tissue factor data are in a Mike Freeman paper that just appeared a month ago in Journal of Infectious Diseases. I'm sorry I didn't include that slide, but it does. CD8 T cells and monocytes co-localize in the SIV positive vascular endothelium, where we think they participate in the formation of plaque. So what's the outcome of all these inflammatory events at the vascular surface? These are SHIV positive rhesus or SHIV negative rhesus, and what we see is there's decreased expression of KLF2, an anti-inflammatory mediator in the rhesus endothelium, and these are the summary data on the SHIV positive and SHIV negative rhesus endothelium, and low levels of the vascular relaxant, endogenous nitric oxide synthase in the SIV positive, SHIV positive endothelium, and these are the summary data in the rhesus positive and SHIV positive and SHIV negative rhesus. So what can we, is there a way that we can look at human plaque cells, the cells that we think infiltrate that plaque? It's not easy to do. We've not been able to do this yet on HIV positive individuals, but we have been able to do this on carotid endarterectomy samples from HIV-negative people who have atherosclerosis. And what we can do is first we can look at the plaque itself, and we can see the presence of CD8 T cells in the plaque and fractalkine in the plaque and IL-15 in the plaque. When we did these studies, we got peripheral blood cells from the same individuals who are undergoing the endarterectomy, and we could compare the phenotype of the blood cells with the phenotype of the cells that localized in the plaque. So this is just showing the events that we get on the flow cytometer. We gated on the CD45 positive cells, which is a marker for cells of immune myeloid and lymphoid origin. We can look at the lymphocytes and gate on the CD3 positive cells in the PBMC and the plaque. And we can gate on the CD8 positive cells from the CD3 in the peripheral blood and in the plaque. What we found in these atheromatous plaques of HIV-negative humans undergoing carotid endarterectomy are elevated expression in the plaque of fractalkine, CX3CR1, and elevated expression of interleukin-15, here versus here. And these are the summary data on fractalkine in the normal parts of the vessel versus the atherosclerotic parts of the vessel, IL-15 in the normal parts of the vessel and the atherosclerotic parts of the vessel, and CD8 T cell accumulation in the endothelium in the atherosclerotic part versus the normal part in these human studies. When we pulled these cells out and then examined them by flow cytometry to look to see what they look like, what we found is that the CD8 T cells in the plaque were enriched for expression of CD69. Remember, that is a tissue resident marker that is upregulated by exposure to interleukin-15. And they had diminished expression of CX3CR1. Remember, that's the fractalkine receptor that allows these cells to home to the endothelium. So when we look at the peripheral blood cells, this is the CX3CR1 density in the PBMC, and it fell in the plaque, and these are the proportions that are identified in the plaque, and these were the Cleveland studies, these were the Moscow studies that were done by our collaborators where these proportions went down. What does it mean to have low expression of CX3CR1 on a CD8 T cell from a person? Well, when you incubate cells with fractalkine CX3CR1 versus incubating them in medium alone, and we look at the cells that are CD57 positive or CD57 negative on the x-axis, and look at the density of CX3CR1, this receptor gets internalized and down-modulated when it binds fractalkine. So you can see here all these cells are CX3CR1 positive when they are exposed to fractalkine, that they get down-modulated. And this is well recognized. These data just are there for you to see this. When we look at, compare these cells taken ex vivo from peripheral blood versus plaque, this is what it looks like. In the peripheral blood, we have lots of CX3CR1 positive cells. In the plaque, they have virtually all lost CX3CR1 expression as summarized here. So here's the model. Oh boy, you guys are in big trouble. I've got lots of time left. This is the vascular conspiracy that we're trying to promote. This is a blood vessel. This is the endothelium on one side. Here is a monocyte attracted to the endothelium by CX3CR1 expression. Here's a CD8 T cell attracted to this endothelium by CX3CR1 expression. HIV, oxidized LDL, bacterial lipopolysaccharide can all activate this monocyte. This monocyte will upregulate tissue factor expression. Some of this is mediated by tumor necrosis factor, elaborated by this CD8 T cell that I failed to show you before, but is published and probably real. This results in activation of the coagulation cascade that elaborates thrombin cleaves prothrombin into thrombin that activates CD8 T cells via binding and cleavage of PAR-1. These CD8 T cells get activated by thrombin, by interleukin 15, by prior exposure to CMV that results in their maturation and the elaboration of a cytolytic phenotype. And here they are in a position to either damage the plaque, damage the endothelium, or participate in the formation of plaque by activating these monocytes. So, turns out I do have a little more time. I wasn't sure that I could talk about the last question that I wanted to pose, which is, why do these expanded CD8 T cells persist in HIV infection? Why do they stay so expanded? They're terminally differentiated. They're CD57 positive, they're CD28 negative, they're fractalkine receptor, CX3CR1 positive, they're inflammatory, and they're thought to be not very interested in cell division, much like a senior faculty member, for example. They are expanded in CMV co-infected persons, primarily only in CMV co-infected persons and persons with HIV disease. And so what sustains their numbers in vivo? They're said to be apoptosis resistant with high level expression of BCL2. I heard that said today. Are they inert? And by that I read senescent, which is what they're typically called. Or do they maintain cell numbers in response to constant production of CMV antigen, which we know takes place because CMV is not a quiet virus. It's expressed frequently in a variety of tissues, even in people who are not symptomatic. Or do they maintain their cell numbers via exposure to a cytokine or by some other means that we haven't yet defined? So to explore this a little, we took peripheral blood cells from humans, and we sorted on CD8 T cells that were CX3CR1 positive, and then we sorted them into 3 different populations. CD57 high, CD28 negative. Those are the classic senescent cells, because CD57 is said to be a senescence marker. Cells that are CD57 low and CD28 negative. And cells that were less senescent, which would be CD28 positive, CD57 negative. And in some of the figures, you'll see them expressed as blue, magenta, it's a good color, and orange, and I'll tell you what they are in each instance. So these cells are not inert. These are the 3 different populations: 57 negative, 28 positive, 57 negative, 28 negative, 57 positive, 28 negative. Those are the ones we're calling senescent. When we look at all these cell populations, which ones are undergoing cell cycling? And the answer is these. The ones that we're thinking are senescent. So they're cycling. They're not inert. Are they somehow resistant to apoptosis? Well, we'll look at this in 2 ways. First is, that's typically characterized by high level expression of BCL2. Their BCL2 expression, and this is in fluorescence intensity, is no greater than that of the 57 negative, 28 positive cells that are thought to be able to respond to co-stimulation. A little higher than the 57 negative, 28 negative cells, but no higher than these. They're not BCL2 high, and they are cycling. So if they're cycling, what are the possibilities that could be driving this? They could be driven by antigen exposure, or they could be driven by cytokines that drive cells into cell cycles. So let's first look at their surface co-receptors. The first one is CD25, which is the high affinity receptor for IL-2, and we can see that they do not have much CD25 on their cell surface. They could respond to interleukin 7, which is a very important homeostatic cytokine, drives T cells into cycle and proliferation. And here we see the 57 negative, 28 positives are very high for CD127, the IL-7 receptor alpha chain. The 57 negative, 28 negatives are intermediate, but the guys we're interested in, the ones that are expanded in HIV disease, 57 positive, 28 negatives, they don't express much CD127 at all. But they all do express CD122, which is the beta signaling chain that's used both by IL-2 and IL-15 for cycling. So they might be able to respond to IL-15, so long as the IL-15 that they see has that alpha chain, which typically is expressed when IL-15 is expressed. Let's see what happens in vitro when we try to get them to proliferate and survive. These are only, I'm only showing you one of the six plots of the, and we're talking here only about the fractalkine positive, fractalkine receptor positive, 57 positive, 28 negative cells, the ones we're most interested in. The first thing we're looking at is whether or not they live after they've been sorted and allowed to survive for a couple of days. This stain is a stain for live and dead. Live's on this side, dead's on that side, to the right. These cells do not survive ex vivo very much. They're, in medium alone, they're mostly dead. If we give them IL-2, it keeps some of them alive. If we give them IL-15, it keeps some of them alive. But if we give them T-cell receptor stimulation, they don't make it. So they are not death resistant, and T-cell receptor stimulation does not do anything good about that. When we look at the cells that are still alive and we look to see whether or not they proliferate, so remember proliferation is going to the left, moving that way, dilution of dye. In medium alone, nobody proliferates. With IL-2, nobody proliferates. With IL-15, some cells do proliferate, and with T-cell receptor stimulation, some cells do proliferate. Those are the guys here, the ones that did not die. Most of them will die. So, what's going on here? Well, IL-15 and T-cell receptor stimulation sustain mitochondrial numbers, as shown here by MitoTracker green. IL-15's in red, T-cell receptor stimulation in green. They maintain mitochondrial potential difference. T-cell receptor stimulation does that. IL-15 does that. IL-2 does not. But only IL-2, IL-15 is capable of upregulating c-myc, which none of these other stimuli do. So, what sustains the expanded, largely CMV-reactive, terminally differentiated CD8 T-cell population in chronic HIV infection? We think that they are sustained by exposure to IL-15 and not by exposure to CMV peptides or other antigens. These cells are inflammatory, they're cytolytic, they're capable of homing to the vascular endothelium, where we propose they interact bidirectionally with monocytes to drive plaque formation. We don't call them senescent, but rather inflammescent. And the role of CMV. What's the job of CMV in all this? We know that epidemiologically, both in the HIV-negative population and the HIV-positive population, cytomegalovirus infection is associated with a greater risk of morbid outcomes, including cardiovascular disease. So we think in HIV disease, together with IL-15, it drives CD8 T-cell expansion and promotes CD8 T-cell differentiation. We know that in vitro, it can infect endothelial cells. And if we take a look at plaque taken from HIV-negative individuals, we can find CMV DNA. And we know that the levels of CMV DNA in plaque are linked to indices of T-cell activation and cardiovascular risk. What we don't know yet is whether that CMV is expressed in those endothelial cells or in the monocyte macrophages that are in the plaque. So we don't know which cells in the plaque express CMV peptides in vivo, and we're hot on that, trying to sort it out with a variety of methods. And we do think that vascular damage could be mediated through immune recognition of CMV peptides, but we think it's more likely that there are other mechanisms that are not TCR dependent that are responsible for the damage that CD8 T cells confer on the endothelium. And so if that's the case, the question is, are the immune specificities or determinants of CD8 T-cell activation at vascular sites dependent upon what they recognize, or are they irrelevant? Are they irrelevant? We propose the latter, but we don't know that yet, and that's a product of ongoing investigation. So this is the model that I showed you before. CMV is there too, IL-15 is there, tumor necrosis factor is there, thrombin is there. It only tells us that, if we're right, that immunology and cardiovascular disease are pretty complicated, but I don't think anybody would argue with that one. These are the people who contributed to this work. Much of this work was led by Mike Freeman, who's a junior faculty member now at our place, was a postdoc with me. Suhail Yunus did a lot of the IL-15 work on the lymph nodes. Nick Funderburg and J.C. Mudd used to work at Case, but now they've gotten their own lives and their own jobs and live somewhere else, and we're not allowed say their name, except I just did it. These are a number of people who've been helping with us in these projects from a variety of institutions. These folks at Case, these folks here at other places. Jake Estes did a lot of the histology on the lymph nodes. Sarah Janela helped us a lot with the CMV issues. And we have a collaboration in Moscow led by Elena Vasilyeva, who have taught us how to isolate cells from plaque and have done a lot of the work that I just reported here. So that's it. I've got time for some questions. I'm on time. Thank you.
Thank you, Michael. I think we have time for 2 or 3 questions before coffee break. So, who would be the first one, please?
Mike, my question, always worried about CD8 activation in the context of effective antiretroviral therapy and what the drivers are. And I'm always intrigued by the result of the group at UCSF, I'm blacking out their name, Hiroyo Hatano, who showed that if you take elite controllers who have a very low level of CD8 activation and you put them on antiretroviral therapy, you diminish the level of CD8 activation. Antiretroviral therapy only impacts, theoretically, viral activity. So my question is, to what extent do you think CD8 activation has been driven by viral activity?
Yeah, so I think there's, as best as I can tell, viral replication in the setting of untreated infection is linked to magnitude of CD8 T cell activation. Some of this is direct, some of this is not, and some of this is very indirect and is mediated by characters like IL-15. So let's say, for example, we're talking about a lymph node. The lymph node is filled with virus. Virus is activating myeloid cells to express interleukin-15 that itself has an effect on CD8 T cell activation, maturation. So the conundrum or the aspect of elite controllers is that their level of immune activation is typically a little bit higher than somebody on antiretroviral therapy. So it tells me, at least, that the antiviral drugs that we have are a bit better at controlling viral expression and viral activation than is our whatever it is that characterizes all these elite controllers. And it's not too surprising that giving antivirals to an elite controller diminishes the magnitude of activation, some of which is direct, some of which I think is indirect.
Thank you, Michael, for a really nice talk. What I would bring up is talking about senescence. It's actually a senescence secretory phenotype. So in terms of which are these EMRA cells, so do you know what do they make in terms of inflammatory mediators at the level?
They make lots of TNF. They don't make a great deal of interferon gamma. And beyond that, we haven't characterized their production of a whole array of cytokines. That probably should be done. But we were looking in this particular experiment to see what might be driving monocyte tissue factor expression, and it turned out to be TNF.
And from the aging perspective, which is what I brought up that point earlier, is those SAS CD8 EMRA cells are actually making IL-18, which seems to be their main mediator that characterizes them. Yeah. And it's MAP kinase driven. It's a P53 MAP kinase driving that phenotype.
And is this spontaneous, Alan, or did they have to be
They can make it as well on their own in an aging.
That's great.
So there is some differences, and I think that's where the links of what we need to define from what I was referring to earlier in the aging field and the HIV field, where we need to kind of make the links on what the difference.
Fair enough. I think the shift in understanding that we're trying to push about these, quote, senescent cells is they're really not senescent. You can call it, they're certainly CD57 positive, they're certainly CD28 negative, but they're cycling, and they're not really incapable of it. They actually do it. And whether that's responsible for sustaining their numbers over time, we don't know. We're proposing that that's the case. Here's a question. Maybe somebody here knows the answer. What's happened to Timothy Brown's CD8 T cell numbers now that he's cured? Where are they? Does anybody know? Or the London patient, or the other patient reported from Dusseldorf? Did they go? Because I don't know. That might be an interest. Because in our treatment, those numbers don't go down.
The only time I've seen CD8 numbers go to normal levels are in Catherine Luzuriaga's infants who were treated very, very early. Still on antiretroviral therapy, but they have levels of CD8 activation that are indistinguishable from uninfected individuals.
So that's fascinating for several reasons. First off, in her pediatric population, they might not have gotten CMV yet. So they may still be CMV naive. And they've got, I suppose, also a different maturation phenotype as they get older than from real adults like you and Alan.
Have a coffee break, Esther? Yes? Okay, so we invite everybody for the coffee break, and thank you again, Michael. A great presentation.